is entitled Flow Meters for Water and Wastewater Applications. And today, in our brief time together, we're going to have only about a half an hour or so to review a whole host of goodies here. So today, we're going to just review water. We're going to review wastewater. We're going to review the different types of technology of metering that you would use for these particular applications, the economics of these, and the limitations of the different technologies. And of course, in conclusion, the calibration and the services and the maintenance of such devices here. So we start off, water as a resource. And it's all about the water. It covers about 70% of the earth, and it's vital for all the known forms of life. About 96% of the planet is found mostly in the planet's water is found mostly in the oceans, and the rest is in the groundwater, glaciers, ice caps. And as we said, it's a key ingredient to life on this planet. And throughout the evolution of mankind, man has thought out means to harness the power of water and tools to control and to monitor it. So the big question is, what do we do when we run out of water? And this is a fact in some places around the world today. And if you're in the United States today, just in the western portion of this country, there's been a drought for a while. And there's many, many states out in the west that are having a hard time with the water. There's been extended drought, and there'll be a drought for some time to come. So the question is, as I said, what do we do when we run out of water? And what we can do in our industry is we can come up with technology to help us inventory the water that we have, control the water that we have, limit or batch the amount of water that we have so we can optimize the usage, so we can reduce the waste of the water through leakages and just mismanagement there. And us, as a consumer, we may have to limit the amount of water that we have. I mean, as I said, out west there's certain facilities there that can only use X amount of gallons of water before they turn it off. So in order to do that, you need to have tools, you need to have equipment, you need to have instruments to monitor that. So as we begin to talk about water applications, there's a host of different type of meters that will monitor water, and we'll touch on some of these today, and they'll include the turbometer, impeller meter, and the good old PD or positive displacement meter, magnetic meter, orifice, a differential, and of course ultrasonic transit time flow meters for water-like applications. And where will we use this technology? Well, at the volume level that we're going to monitor the water, there are going to be water treatment plants. So even though we collect the water, we harvest the water in some fashion there, we have to condition the water to make it drinkable. So it has to be processed. And then, of course, we have to get the water from certain sources there. So you can get it from irrigation, you can get it from wells, you can get it from the groundwater, the aquifer, you can get it from desalinization. So there's a whole host of methodologies to collect the water. Then we have to manage the water. So we're going to go through a municipality or a city water distribution system. Then the water is going to come into your building. You need to monitor the water coming into your building, and then say you have tenants inside this building. We need to submeter the waters into individual users. So as you can see, the tools for monitoring water are exponential today as they were before, and there's many, many different methods to do that, and we're going to go over some of those guidelines. Now, one red flag that's changed our world here in the last year or so is in the good old days, you said, yeah, I want a water meter, and we'd say, okay, here's the model that you want. Now, when you ask for a water meter, we have to define what the water is used for. Are you going to consume the water? If you're going to consume the water, then there are new rules and there are new regulations. I'm far from an authority on this, but basically it's all about the lead content of materials of construction. And so the NSF has delegated some requirements. So as of January 2014, there's certain levels of equipment that meet the Safe Drinking Water Act. So there are different types of flow meters that you, the consumer, may not be able to see the difference from the outside, but the inside, they're different. And so if you're buying a technology that is for a consumable water, something you're to eat or drink with basically, then it needs to be NSF certified. And it really comes down to materials of construction. So we brought the water in, we use the water, we process the water, and now we have wastewater. So we have to dispose of the wastewater. But it's still water. In this case, it's usually bearing other materials along with the water. What better way to comply a picture of describing wastewater? And in the wastewater industry, there's different methods for monitoring flow, and we'll break them down in different categories. The most popular category, the first category, would be a closed full pipe, traditionally pressurized. You can use different type of metering now because you're now going to monitor a volumetric flow. So you would use a magnetic flow meter or an ultrasonic transit time flow meter or an ultrasonic Doppler type technology. And the other application that you're going to use for water and wastewater applications are pipes that are gravity fed or traditionally partially filled pipes. So there's no pumps in the system, or there may not be pumps in the system as it flows down the line and may be collected at a lift station, or open channel applications. And to solve these problems, you can use the good old Flume or Weir and just measure the level with a tape measure or a ruler, or you can use ultrasonic level, and you can measure level also by monitoring pressure to measure level, and then using say like the Manning equation to calculate how the liquid's falling downhill, an area velocity method, which combines both level and velocity to calculate a volumetric flow. So you can see there's just not one solution for all flow metering applications, especially in the water and the wastewater industry. And as here's examples again of the different applications for closed and open channel-like applications. Wastewater treatment plant would traditionally have closed full pipes, and then of course to get to the plant they're going to go through a series of lift stations to get to the plant. So a lift station is basically everything flows downhill to the plant. So you basically, a lift station lifts up the wastewater, pumps it out, and then it goes some distance down the hill, so to speak, until it gets to a point where we need to get to the facility itself. So sewage itself is a wide variety, but most part, majority of it's water for our sewage applications in most cases there. So we need to treat that and reprocess that. Open channel applications, again, it's a gravity-fed applications, and perhaps the most common and undiscovered application, at least monitored, is the building effluent. So if you have a facility that's discharging from the building, you normally build the gazinta equals the gazauta, so to speak, in most cases there, but in many cases that's not true if you're using manufacturing or other repurposing processes within your facility. So people actually begin to monitor the effluent of their facility and getting comped for differentials between the influent into the facility. So flow metering, clean water, dirty water, repurposing of water is still a vital resource. When you're done processing a wastewater, it goes back in the river and it goes back into your water processing system. So it's just a circle that goes around and around and around, and we need to economize with that. So what do? We start off with Brent's pet peeve question. It gets all the time and every day of the week. And here, of course, we're specializing in flow meters, and one of the things that we do a lot is we do flow surveys and rent equipment using ultrasonic meters to test water meters. And the old question we get 10 times a day is, I don't like that city water meter, and I'll be darned that that's right. I'm sure it's reading high. And then they'll call up the city and yell at the city, and the city will come out and replace that water meter, and gall darn ya, that city water meter will now read twice as high as the old water meter. So just a hint to the wise, if you got an old water meter, and as long as they're not screwing up with the calculations of how they're deriving the data there, you got an old water meter, it's reading low. The older it is, the lower it's reading, don't change it. You change it, your bill will go up. Now, with the second thing that comes in mind is they want us to verify water meters all the time, which is fine. So there's a water meter coming in from the city services. We're coming into a facility, and in the basement of that facility, we'll put another flow meter. The gotchas about that is most people don't understand the technology of volumetric flow, or even break it down further, the velocity of the liquid itself. So if you're coming into a building and I've got an 8-inch city water line, and I come into the building and we go ahead and put a traditional flow meter, any kind of flow meter in most cases, on the 8-inch line, even an ultrasonic flow meter, which can monitor pretty low flow rates, mind you. We'll go do the flow survey, and the guy will say, okay, I'm going to go and use some water. Let's see if you see it on your test meter. So they'll leave the basement, go up, and come back in a minute, and they said, did you see that? And we'll say, no, we're on this 8-inch line there. We didn't see anything. He said, well, I flushed the toilet twice. Now, 1.5 gallons times 2 is 3 gallons in an 8-inch pipe. And in an 8-inch pipe, 3 gallons is not going to blip up on the radar. 3 gallons is like 0.01 feet per second as a reference. So most flow meters don't go that low. So you won't see a toilet flush, you won't see minimal use on a large city water meter application, and there's the difficulty in monitoring that application. How does the city do that? Well, they don't use a traditional 8-inch meter. In most cases there, what they do is they'll use a compound water meter. Now, a compound water meter is 2 meters. And a compound water meter basically is a big meter and a little meter. And the little meter basically, what would we say about velocity? The smaller the line size, the higher the velocity. So I might be able to pick up that toilet flush if I've got a 1-inch or 1/2-inch line monitoring with a traditional flow meter. But my reference meter we just talked about is an 8-inch line. So it's an apple and orange comparison. So if you're going to do a flow study and you're interested in low flow monitoring, then you had to have a like information. So to compare against a compound meter, you can monitor the 8-inch compound meter, but it also has a sidecar. It's got a small and usually a turbine flow meter that's monitoring a smaller line size. You won't have any ability to reference it. So that's an issue there. So if you wanted to monitor a big water line, know your minimum flow rates before you go in and get yourself into trouble. Now, the other types of meters, and I said there's just a plethora of meters. We're just going to go through some conventional technologies here to get you oriented. So again, on the water meter side, something that you're going to use for a drinking water application, again, make sure that it's NSF certified. Here's a typical example. This would be called an impeller meter. It looks like your traditional water meter, with a little sweep pan and the odometer. This uses an impeller that's gear attached to the display itself. So when it goes in, the wheel turns around and it makes the odometer monitor. So this is just a conventional method that's been around for a long time. The economics are relatively inexpensive, and of course their prices are based upon pipe size. Perhaps even more popular is the PD meter. And the PD meter, again, you probably see this on the outside of your house. Again, a sweep pan with a digital display, and the PD meter basically measures flow against a previously measured volume of liquid, and it's held in a small chamber. The flow rate is calculated against the number of times the chamber is filled and emptied, and then the data is recorded through either a nutating disc or a piston mechanism that drives that display there. It's kind of like a clock for a bad description. So this is the basic technology, and again, these are sized by flow rate, and they come in a wide variety of different line sizes. They're traditionally around from 1/2 inch up to 2 inches, and of course they'll make some larger ones for unique applications. Now, we talked before about submetering, and submetering is just the breakdown of the network here. So we're getting very granular. So as we said, if you had the individual tenants, you had individual zones, you might want to monitor for billing purposes those individual people. And so for that reason, the economics have dropped because the volume of meters is staggeringly high now, so exponentially higher. So we don't want to spend a couple $100 for a water meter. We want to spend $60 or $80. And so now you can get a plastic, a single jet flow meter, the traditional 5/8 times 3/4 inch plastic body meter that meets your requirements, and you can use it everything from your variety of submetering applications your commercial buildings, marinas, RVs, and the list goes on and on. You can get it with a display, and then most of these devices we just looked at there, you can probably get a pulse output, so you can use the pulse to go to some remote information or remote counters should you need to do that. And then, of course, there's just the traditional turbine flow meter. And a turbine flow meter, as everybody probably knows, is basically a turbine turns around and has a magnetic pickup, and it creates pulse. And those pulses or frequencies are proportional to the volume passing through the turbine. And now we move from the traditional water meters more into the process meter, and the turbine has different variations. It comes in sanitary packages and non-sanitary packages. So now you're wandering into the arena where you need to make sure you're at the right specifications and the right certifications for the specific application you're looking for. The other side of the coin, getting into more process, is the world of magnetic flow meters. And there's been a massive explosion in magnetic flow meters in the last few years. They come in all different shapes and sizes. You can get them in an insertion probe. You can get them in a plastic battery meter. And you get them in small little line sizes. So they come in all different flavors, shapes, and sizes. So again, what are you going to use them for? So there's some that are certified, and there are many that are not certified. So again, select the meter that you need for your particular application. And the reason for the mag meter is so interesting is it has really no obstruction. So there's no real pressure drop in most cases there. And the accuracy is quite good. So the accuracy of a mag meter at your low flow and high flows are very good. And you can get anywhere, a tenth to 1%. The process liquid must be conductive. So it's got to be water-based. So depending upon the brand, you have to measure the conductivity in micromoles or microsiemen. It's anywhere from 2 to 5 to 20 microsiemen and up. So if the process liquid is conductive, it works great. Mag meters do not work on the hydrocarbons, as an example. The hydrocarbon is not really conductive. So that's the gotcha between where the mag meter works and doesn't work. Mag meters, you traditionally need a little bit less straight run of pipe than most meters for optimum performance. In fact, there's one particular brand we have that actually only needs 1 pipe diameter and 0 after, and it uses a special method of averaging to come up with multipath to come up with that. So again, a mag meter is priced based upon the diameter of the pipe size. So a 1 inch is going to be less expensive than a 10 inch. And then we also got they're made of big hunks of metal there, so it's a hardy device there. You're getting in the 50, 60, and 100-pound weights for mag meters when you get into the larger line sizes, and you may spend more money with the crane installing it than you will cost of the meter itself. So you pick the mag meter based on the application, and then now it's wetted, and you're going to get more into the process size, and they have different liners. You can get a rubber liner, you get a Teflon liner, and different electrodes. So it's all based upon your process liquid. And then just touching on how a mag meter works, as we said, it's limited to conductive liquid applications. And go back to grade school, you probably learned the Faradays Laws of magnetic induction. Basically, his laws basically state that we're going to take this pipe there and we're going to run a conductive media through this pipe. And inside this pipe, we're going to have 2 electrodes, kind of like a voltmeter. We're going to put them in the side of the pipe. They're wedded to the pipe. And Faraday's law basically states that if you run a conductive media through a magnetic field at right angles here, you basically create a current. And the way we get the magnetic field is we wrap around this pipe with copper wire. Remember back again in grade school where you took a nail and you wrapped the copper wire around it, and then you attached it to a battery. And lo and behold, the nail became a magnet. So we make this a magnet, and that magnetic field is like a curtain, and when the conductive liquid goes through there, it creates a current. The electrodes measure it just like a voltmeter, and that is proportional to flow. The more liquid that goes through there, the greater the current. So Faraday's laws of magnetic induction have been around for a very long time, very active parameter. The law does not work if the process liquid is not conductive. So then we go into the world of Clampon technology. And a Clampon technology is kind of neat because you don't cut a hole in the pipe, you don't flange anything in the pipe. So your installation costs are zip basically. You're just going to wire it up, and that's that. So you don't have to bring in the crane to bring in the 18-inch mag meter and cut pipes and all those different things there. And it comes in different flavors. And so the ultrasonic Doppler flow meter is a technology that's been around for a long time, but very confusing. A Doppler flow meter works like police radar. Sends in a sound beam, bounces off your car, sends a signal back and says, this is how fast this car is going. So on a Doppler flow meter, what you need to have is suspended particles inside the process liquid. It actually needs to be a chunk of stuff. If there's no chunks of stuff, then the Doppler flow meter doesn't work. And depending upon the different variety of manufacturers here, generically speaking, you need to have about 100 parts per million of suspended, and that's a key word, suspended solids, not dissolved solids, of particles that are 30 microns or larger. So no chunks of stuff, the Doppler doesn't work. So the Doppler is relegated traditionally to the wastewater industry, and you'll find it in some surge applications and typically in a lift station application with shorter runs of pipe, and then the plant itself with the heavy level of solids, and of course the sludge effluents and things like that. So that's the Doppler flow meter, and there are different tools to monitor it. You can monitor it with a portable device, and there's handheld devices, just as one example of many different that are out there. You can spend as low as $1,300 and a lot more than that, as much as $6 grand to get a portable Doppler flow meter. And it's all about the specifications and what you're going to use it for. But this particular model here is a handheld device that you basically hold the sensor on the outside of the pipe, and it basically will monitor applications a half-inch and larger, and you can program it to read directly in gallons per minute. And if you want, you can actually log data and leave it there for a while. So these are traditionally battery-powered meters that do that. On the other side of the coin is the dedicated technology. So now we're going to look at a wastewater treatment plant raw influent or sludge application or a lift station application. And in this case there, we want a dedicated device. So we're still strapping on a sensor on the outside of the pipe. The device itself would then begin to read rate and total, and you can transmit an output. You can transmit contact outputs to drive a sampler. You can transmit out a 4 to 20 milliamp. You can use that for control. You can use that for your SCADA system. And then in addition to that, if you want to have a standalone data collection system, you can have a data logger to the device. And so you can store the data. Nobody uses circular chart carts anymore. Well, some people still use circular charts. I don't know what they do with the paper. They just put them in a drawer. But if you want to collect data and put it on a spreadsheet now, as opposed to a circular chart, you can store it on the meter, plug in a jump drive, collect the data, and then go later on and store it on a computer, or just print out your piece of paper, your spreadsheet, and put it in a drawer. The other side of the coin is the clean liquid ultrasonic flow meters. And the clean liquid ultrasonic flow meters are called an ultrasonic transit time. Now the transit time is a more accurate beast than the Doppler. And the transit time variations are, it works on applications with no suspended solids. So sewage is a strange beast. Sewage is traditionally water. Residential sewage is water. Most commercial sewage is just water. A couple little chunks of stuff, so to speak. So transit time technology will work on sewage. Transit time will work on ultra pure liquid applications like deionized water, jet fuel, well water, drinking water, sewage, but it doesn't do a very good job on sludge. So transit times traditionally work on ultra pure liquids up to about 2% suspended solids, which is now in your sludge and oatmeal category. So transit time will do sewage. The Doppler will usually do sewage unless it's all clean liquid, or you have some turbulence or aeration from a pump. So lift station applications are usually okay for a Doppler. And a lot of times the straight run of pipe is not long enough for a transit time flow meter on a lift station application. And the way a transit time flow meter works, we basically have the signal coming in from the left to right. We send a sound beam across the pipe from the first sensor to the sensor downstream. We measure how long it took. The second sensor sends a sound beam right back, but because I'm going against the flow, I'm going against the headwind, it takes a longer period of time. The differential of time between the two sensors is the coefficient, how we derived and how fast the flow is going, and then we calculate the volumetric flow. We have different configurations. The transit time, you traditionally see it in this configuration is called the V, or the dual path configuration. We traditionally use it in applications from half to, say, a 24-inch pipe. Larger pipe sizes or crustier 50-year-old nasty pipes that have poor sound conduction, we use the Z or the single path configuration. Same thing there, a little more power, not as fun to install. And as I said, for a proper installation, this technology needs about 15 pipe diameters of straight run of pipe, which is the traditional straight run of pipe for most flow meters, 10 and 5. And that's why sometimes a lift station application can be problematic for this type of device. Then we go into some of the tools that uses ultrasonic transit time flow meter. In this case there, we have a portable, handheld transit time flow meter, and there's a host of different brands out there, so you need to pick one that meets your budget and your data recording and your accuracy requirements. But this particular meter here is one of the newer technologies that has a single-piece transducers. You get a sensor from 1/2 to 4 inches and another sensor from 2 to 48 inches, and they're on a rail, so you can literally hold the sensor on the pipe. So you can do spot checking, or if you want to leave it there to do a flow study. Finally, we have a device that the data logger works. And so basically it stores all the data on an SD card. And the SD card, that card that you put in your new camera, it's a 2 or 4 gig SD card, which basically means you can store data until the cows come home. So there is no longer a capacity problem as the old data loggers. And you don't even need to use any software. You just take out the SD card because the file is saved as a CSV file. So you slap it in your laptop or your PC and turn on Excel and open the file. There's no software, there's no cable, and you're not going to pull your hair out using the data logger. So the technology is moving forward in the data collections. It's got screenshot saving, so you can press a button so it stores the data. So select the portable ultrasonic transit time flow meter that suits your need. There are some that are in a big NEMA 4 weatherproof suitcase that you want to leave sitting in the mud, or there's ones that they're handheld. You can walk around and go from pipe to pipe to pipe to do your water studies. Now, here's a beast that is a ultrasonic transit time and an ultrasonic Doppler. It is a hybrid, and it has both cans of soup in the same pot here. And basically, you have the ability to monitor as a transit time flow meter and a second set of transducers. It's not the same set, so it's basically 2 flow meters in one box. And if you were to put both on the same pipe, it would default to transit. When the transit didn't work, it would go to the Doppler. In most cases, this is not necessary, but if you wanted 1 meter to go into a wastewater treatment plant to monitor your water, your sewage, and your sludge, this is the guy. This is also kind of cool from an electronic technology basis there, because it's basically a laptop. It's a Windows-based technology with a swipe screen operation, so those iPhone users won't need any training. So it's the latest technology, and it's using some very interesting transit time processing. The gotcha is it's kind of big and bulky, so it's not a real handy-dandy portable device there, but if you want something that does everything, that's one technology. Now, the dedicated technology continues to be very budget-oriented and price point. You can now buy a dedicated transit time flow meter for about $2,300 bucks. So that makes it very economical as opposed to using an inline device. Again, it's a transit time flow meter that does need the straight run of pipe to do a good job. And now what's also happening is we need to say hello to our flow meters. They're not all standalone, and we'll have a building automation system. And so the communications to say hello to this meter are very interesting. So if you have something that's using Modbus, RT45, or if you need something that's using BACnet, something that's using Ethernet, the communications are there, and you can just plug in the meter, and you'll have the communications you want to communicate to your building automation system. So again, it's making accessibility to sub-metering very practical, economical, and adaptable. So now we walk into the pipes that ain't full. And an ancient technology was called a flume or weir. And the flume is basically traditionally a fiberglass device there that's an artificial water channel is a good way to describe it, to form a gravity chute. And if you look at the different shape of the flumes there on the bottom there, and mathematically designed to represent flow based upon liquid level height. so as the liquid goes inside this flume, there's a ruler here, and based upon the height of the liquid, it will tell you, you can go to a reference guide, it'll tell you what the actual flow rate is. And so we've derived different ways to use that technology. So the first method to use that technology is, instead of getting a ruler, let's use a non-contact device to measure that level. So step one, we need a ultrasonic level sensor. So an ultrasonic level sensor, basically, again, kind of like radar, sends a sound beam from the face of the sensor and reflects off the liquid surface, comes back to the sensor, the change in frequency, and from that we can calculate the level of the process liquid. So the next step after we do that, we need to put some math into it. So in this case there, we just said before, if we had a flume, or in this case there, a weir box with, say, a 90-degree notch cut, V-notch cut in the front of the weir box there, basically by monitoring the level in that weir box with your tape measure ruler, you know basically what the flow rate is on that particular application. But if you were to put an ultrasonic open channel flow meter, or it's an ultrasonic level sensor with the math module over top of this weir, measure the level, and then punch in on your keypad that I've got a 90-degree notch here, it will calculate the volumetric flow by just monitoring the level. And we take the same technology if we were to go in an open channel application. In this case there, we'll have a pipe. So we have a sewer pipe application, which is a gravity-fed application, and therefore we're not going to have a full pipe. So we're going to have some flow in the pipe there. So we need to put a defined shape. In this case there, we can put our flume, and they come in all different shapes and sizes, Parshell, Palmer Ballast, and the list goes on. And they're all calculated basically by when the liquid goes in there, it elevates it to a certain height. We add the ultrasonic open channel over this device there to calculate the head and come up with your volumetric flow. And so the devices to do this are many. Here's one particular device. This is basically designed for the open channel flow metering. So it's a level sensor, but in addition to the level sensor, it has the math module built into it. So if I wanted to put this over my weir with a 90-degree V-notch in it, or if I wanted to put this over a 6-inch Palmer Ballast flume, or a 12-inch Parshell flume, and the list goes on and on and on, you basically, by measuring the level and then selecting the shape of that entity that you're going to call a flume or a weir, it will calculate the volumetric flow. So it's non-contact from an old technology, making life a little easier. And this is just an example of that. Again, you can read flow rate, you can read total, you can paste a sampler with it, and then again, you can use an analog output for your SCADA systems, or you can log the data. Now, the next step is to get some degree of portability. And in this case there, as I said, the technology traditionally used to do that is called an area velocity flow meter. And an area velocity flow meter is used in an application where we really don't have a defined shape. There ain't no flume, there ain't no weir. And so in order to monitor that, you need two pieces of the equation. You need to measure the height, and you need to measure the velocity. And so we have a device that does both. So in this case there, an area velocity flow meter basically has a sensor that in this particular model there, and there's different variations of this, but this one is all ultrasonic. So on the top of the sensor, it's measuring the height of the liquid from the inside out, and this is measuring the velocity of the liquid. And so as long as those two sensors are active, then we can calculate volumetric flow. So this particular type of technology is traditionally used in applications that are, say, 6 inches or larger, and it would use them in a sewer discharge pipe, or other areas you could put them in a channel, a rectangular channel. You can put them in different shapes there. So the geometry to use different shapes there, we need to have the ability to define the area. That's a gotcha. So you just can't throw it in the river and say, let's go. We need to define the area to calculate the volumetric flow. And we do need to have a relatively flat surface to reflect the level on it. And if we have an exotic application, you can actually put a level sensor that looks down from the top. So there are unique variations of this technology, but you can get it as a portable device. So in this case, you're going to come with a battery-powered device that basically you're going to put this sensor in some type of a mounting ring and shove that in the end of a discharge pipe. Basically, this part here in the front is the velocity. This part in the back is a level sensor. And so you can put this as a portable device to harvest the data, log the data, or you can go and put it with a dedicated device, so you're leaving it there as a permanent type of installation, where again we have the same sensor, and this little stirrup would get mounted to a mounting ring, so it doesn't go anyplace, or a mounting plate, again depending upon the configuration that you're going to put the device in. The technology again would read free rate and total, the same outputs we talked about before, and then of course you can log the data, throw away those circular charts. They're such an interesting device. How's that? Now, what do you do when you have a budget? And so you have these big fancy portable devices. What if you're doing an I&I study and you need a half a dozen open channel flow meters? Well, there are some economical alternatives. Secondly, what do you do if you have an application that's less than 6 inches? Most of the area velocity flow meters need to have that minimum height, and they have issues. Now you need to go and use some of the older technologies married with newer technologies. And now we'll measure level by monitoring the pressure. So in using this methodology, this sensor here is a pressure sensor. You drop this down a line and it gets carried downstream. And so on most applications, you don't even have to go in the manhole. And basically what you're going to put into the software, this is a logger and on a module here. This particular portable device, you tie this off in a ladder and drop this down like a fishing line that's going to carry downstream. Basically, you would program this device with the pipe size and the slope, and it will use the Manning equation to calculate volumetric flow. So it's making some assumptions here. So the key here, a Manning equation is an equation that calculates how fast flow falls downhill, basically. And it's been around for a long, long time. Not as accurate as the area velocity method, but an I&I study is mostly about time. It's not instantaneous monitoring. So you can do this as a portable device, and you can buy these things for, I don't know, $1,200, something like that, as an alternative. And there's also dedicated versions of this. As I said, when you get less than 6 inches, your choices for doing open channel flow monitoring are limited. In that case there, you can put in a Flume, you can put in a Weir, which is both are pretty expensive there, or you can use this type of technology, which I believe can go down to a 2-inch line size, and put a dedicated version of the electronics in the application. So there are variations of everything we're looking at here today. This is just a glance at some of the technologies. And some of the tools that you're using in the waste treatment plant, you begin to monitor for energy efficiencies your compressed air. And there's digester gas. This particular device here is for clean applications. So it basically has 2 holes you drill into the pipe, strap the sensor on, and using a thermal method will monitor flow. And then for applications that you have digester gas and dirty gases, we have other insertion thermal devices that are designed for that. So there's a whole host of methodologies that we're really not going to expand upon now on the air side for the waste treatment facilities. Calibration. Well, many of the meters off the shelf, they're factory calibrated, you put it in, you're done. If you install them properly with the proper straight run of pipe and the proper process liquid, you're going to meet the accuracy requirements for most applications and stated applications of the device there, whatever they say is most cases there. Sometimes people want an annual calibration of their technology. What do? So you bought this 10-inch mag meter. I need an annual calibration or recertification of the device. And most likely the meter didn't change, but you need to verify the meter. What do? Well, there are companies that certify meters in the field. There are, in many cases there, you can actually do it yourself. You can rent equipment. You can hire us, or you can find somebody local that does the services there. And a lot of people use non-contact technology, ultrasonic and Doppler, to validate the inline flow meters for annual calibration purposes. So the other alternatives, yank it out of line and send it into a calibration lab. So in most cases there, people don't yank it out of line. You bring somebody to the meter, and there are tools in the market to test the calibration and recertify the device. So the one thing I learned of all the years in working with flow meters is a closed full pipe is always more accurate and easy to work with than a partially filled pipe. So, should you have the opportunity to reconfigure your plumbing configuration, put a trap in the line, and make your partially filled application into a full pipe application. And not everybody has the ability to do that, but in this case there, if you have the choice, do that. You have much better results, and you have a much wider selection of flow meters to address your situation and your budget requirements. So what do we learn? We learned that there's a whole bunch of flow meters that you can use in the water and wastewater industry, and you need to monitor the specific application and select the right device with the specifications for your particular application. There are inline devices, there are high-tech devices, there are non-contact devices, and they're all monitor your budget. You want to get an ultrasonic flow meter, you can get a dedicated one like $2,300. You can get a inline water meter, for 2 inches for $800 or $900. So, you got to cut pipe, you got to install it. What do you got? So these are decisions you need to make. If you need to test the device and inspect for maintenance, a portable device is a great way to go. You can buy portable technology. You can rent it by the week for $699 to rent the device there, or less in some cases there. So the tools are available to the educated, and the tools are available to the people who have never used the technology before, because the training and the ease of use has really evolved in the marketplace today. Just a little glance at one of our R&D flow loops there is engineer Paul Harris before that doing a flow study right there with a mag meter in this particular loop there. Got a whole bunch of toys at our facilities there. So InstrumentsDirect has been around for a long time, and we specialize in flow meters and do have a hankering for ultrasonic and magnetic and turbine meters and PD meters and what have you. So if you have a unique application, what we talked about today on the website, you will find data sheets on many things we talked about today, operation manual, some cases software, in many cases training videos on the product page itself. So feel free to use it as a resource, a knowledge resource. Still can't answer your question? Then what you need to do is give us a shout, and then one of the tech people will say hello to you and take care of your particular application. So once again, Brent Baird has talked too much over my allotted time there, but thank you very much for your participation today. We hope you continue to monitor our emails for our monthly webinar series. Should you have any additional questions, we're going to conclude the audio portion of our program. We will leave the chat open for a little while longer, but if that still doesn't answer your questions, give us a call or drop us an email. Again, Brent Baird for InstrumentsDirect. Thank you very much for attending our program today.